is going to be the first of two on 2-4, simplifying, or not simplifying, but complex numbers and operations, which we are going to start off with looking at simplifying square roots. Now, this is a skill you may have learned in geometry. I just want to go back over it because it does come up in this section because we will be using the square root property to solve quadratic equations where the b value is equal to 0. So to simplify a square root, this is really like reducing a fraction. It's not necessarily incorrect to leave your square root in the forms that I have shown, but it's not going to be the simplest way or the most reduced format of your square root. Think about it like if you have a fraction 3/6, you typically wouldn't leave it 3/6, you would reduce it to 1/2. That's going to be the basic idea here. Now over on this side, you can see some of the perfect squares. It goes up through, from 1 squared up through 10 squared. Now some of the bottom ones are covered by my video screen here, but that's not going to affect the outcome of what we're doing because all of these have perfect squares that are less than 100, which is 10 squared. So any square root can be rewritten as a product of its factors. So if we look at 8, you always want to think about what the greatest perfect square factor is of the number that you have. So perfect squares are things like 1, 4, 9, 16, 25, 36, and so on. So for 8, the greatest perfect square factor is 4. So I can rewrite this as 4 times 2, or the square root of 4 times the square root of 2. Notice I did put the one that was the perfect square first. This is just a habit that I've created, so I remember what comes out of the square root versus what has to stay in the square root. The square root of 4 is 2, so this is going to simplify to 2 times the square root of 2. For 24, the greatest perfect square factor of 24, if I go to my list, is 4, and 4 times 6 is 24. Square root of 4 is 2, so this is 2 times the square root of 6. Notice the 4 comes out and becomes the 2. The 6 has to stay in because it is not a perfect square. If 1 is your greatest perfect square, that means there is not a perfect square factor that you can use to rewrite the question. Just something to keep in mind. For 18, greatest perfect square is 9. This is 9 times 2. So our solution here would be 3 times the square root of 2, because again, the square root of 9 is 3. 48, this is a tricky one because some students forget about what the greatest perfect square would be, and there you can see a few more perfect squares. The greatest perfect square factor of 48 is actually 16. This is 16 times 3. And so this is 4 times the square root of 3. That would be the solution there. If you do pick a perfect square, but it's not the greatest, that just means you might have to break down your non-perfect square factor further. For example, with 48, let's say you chose 4. Well, 12 itself has perfect square factors. 12 has perfect squares of 4, and then 3 is left over. So this is 2 times 2 times the square root of 3, and so you would still get 4 times the square root of 3, even if you didn't pick the correct one to begin with. Okay, these are a few other examples. I'm actually going to skip over those. If you want some additional practice with simplifying square roots, please reach out to me, and maybe we can schedule a tutoring time and go through that. Okay, so that leaves us to 2-4, and I'm actually going to calibrate this again. Hopefully things will be a little more accurate than what they were before. Okay, so complex numbers and operations. So we are going to be looking at complex numbers today, and you'll see what I mean by complex number once we actually get into our lesson. And your essential question, how can you represent and operate on numbers that are not on the real number line? So we're going to be looking at things that previously we could not do. So our first example, how can you use square roots to solve each equation? So for part A, I have x squared is equal to 16. We are going to use something called, boy, this just does not want to quite work out. The square root property. So the square root property means that if you can isolate your x squared in a problem or some quantity that is squared, you can solve by taking the square root of both sides of your equation. The square root of x squared is x. Now you do have to be careful with the square root property though, because of the nature of numbers. Whenever you square them, they end up becoming positive, or rather real numbers, when you square them, they end up being positive. So the square root of 16 is 4, but both the positive and negative versions of 4 would give me that positive 16. So I do need to put down the plus or minus sign anytime I use the square root property. This is shorthand instead of actually writing x is equal to 4 and x is equal to negative 4. So if you just write that, that accounts for both of your solutions. Over here for part B, same kind of question. We have x squared is equal to negative 9. By the way, you can use the square root property anytime your b term is equal to 0. If b is not equal to 0, in 2-5, we'll look at how to deal with that to still use the square root property to solve. So I can take the square root of both sides. Again, the square root of x squared is x, but we run into a problem on the right-hand side. Because I can't take the square root of negative 9 using real numbers. I know I'm going to have a plus or minus because of the nature of the square root property, and if this was a regular 9, it would be 3. However, 3 squared and negative 3 squared both equal positive 9. This is where our lesson comes in today. And we need a new character to represent the square root of a negative. And that's going to be I. I is the square root of negative 1. It is the imaginary unit. It represents the set of all the imaginary numbers. So any time you're taking the square root of a negative, like we have here, the square root of a negative 9, you're going to have an I in your answer, and that I represents that negative, the square root of a negative. Something else to keep in mind about I, because I is equal to the square root of negative 1, I squared is equal to the real number, negative 1. I is the only thing that you can square and actually give a negative. So that'll come up a little bit later, possibly in the video that we do for the second part of 2-4. Okay, so we have some stuff here on imaginary numbers, and I'm going to try calibrating one more time. Hopefully we'll get a little bit better this time. Things are just a little bit off today. Okay, so we'll see how that one goes. So we have some notes here. We have imaginary numbers in the form of bi, where b is some real number that is not 0, and I is the square root of negative 1. So you can see this little script I. I typically make my eyes with a little tail on them so that they don't look like ones. And then you have complex numbers. Complex numbers are the form a plus bi, where a and b are real numbers, and I is the square root of negative 1. So complex numbers have a real and an imaginary part. That's what we're going to be working with throughout the majority of this section. Okay, example 2, how can you add and subtract complex numbers? So part A is asking us for a sum, part B is asking us for a difference. This is supposed to be easy, this section here, because all you're really doing is combining like terms. So for part A, sum means addition, so I would be adding these two terms together. Because I'm adding, I can basically ignore the parentheses. There is a plus in between them, but when I add this negative 11, it still just stays minus 11. So now I match up. The 4 and the negative 11 are the two real terms that don't have an I. That makes the negative 7. The negative 7i and the 9i are the two imaginary terms, and those add to 2i. And that's your solution. Easy. Just go through and add your like terms. Part B, difference, is subtract. Now for difference, I am going to eliminate the parentheses from my first complex number. But for the second one, I do have to distribute that minus to both of those terms. So this is going to become a minus 2 plus 5i. Because we are subtracting the 2 and subtracting the negative 5i, that's why that one becomes a plus. Now, just like before, I go through and match up my terms that are alike. So the 6 and the negative 2 make a 4. The 8 and the 5i make a 13i. So we have 4 plus 13i as our solution there. So this is going to wrap up our first video. In the next video, we're going to focus on multiplication, and we're actually going to do some factoring with I. Factoring with I is very similar to factoring. When you don't have an I, you'll see whenever we get to the second part how that's just slightly different. So go back, rewatch this. Let me know if you have any questions, guys.